Welcome to Math 31. This is another lesson on related rates 2, and I'm going to look at two types of questions, travel questions, and there's actually 4 of these ones, and then also a pulley question. So fairly specific type examples, both illustrating different things that you can do to solve related rate problems that are actually quite transferable to other ones. So I'll probably break this into 2 short videos just because each of the questions take quite a while to do. So the travel questions, very common, one of the more common related rate problems that you encounter. And we have in this case 2 cars are leaving the junction of highways 22 and 12 at the same time. One of the cars is northbound and it's traveling at 90 kilometers per hour, and the other one is headed towards the east and is going at 120 kilometers per hour. We want to figure out at what rate is the distance between the cars changing at exactly 2 hours later. So based on this illustration, if you look at it like this, one's a taxi, one's a car, they're leaving that junction. They're going a fixed speed, so their rate is unchanging, but the distance between them will be constantly changing because they are not going, they're going away from each other at a 90-degree angle. So it is a classic type of related rate problem, if you like. And we, to solve these, do use Pythagoras' theorem again. So we would go calling the horizontal distance x and the vertical distance y, and then the distance between them z, we would go x squared plus y squared is equal to z squared. And then, that's typical for triangles, of course, identify what we're looking for. At what rate is the distance between the cars changing 2 hours later? So we want dz dt at t is equal to 2 hours. Now that's a problem already, because if you take a look at that original equation, we have an x, we have a y, we have a z. We do not have a t. So I'm going to put off this little problem until later. So without doing much more thinking, I will differentiate this with respect to time, and I'll get 2x dx dt plus 2y dy dt is equal to 2z dz dt. And we could divide out that factor of 2 from every term before we get too deep into the equation. So x dx dt plus y dy dt is equal to z dz dt. And then we take stock of what we have and what we're missing. The dz dt, well, that's what we're looking for. The dx dt, okay, well, let's see what we got. Now, dx dt would be the rate of change of the eastbound vehicle. So dx dt is actually given to us. Dx dt, the distance is increasing using the intersection as the reference point, and is 120. We don't use units in our calculation, of course, but it is kilometers per hour. And then you take a look at dy dt. It too is increasing. It's going to be a positive value as it speeds away from the intersection. It's traveling northbound at 90 kilometers per hour. So that's what we're dealing with. So we have both the dx dt and the dy dt. What we need now is a measure for x, for y, and for z. And it's not that big of a deal, because at t is equal to 2 hours, we are able to establish each of those measures because we have the speed. So at t is equal to 2, If you're trying to figure out how far x has gone, well, the distance, x is the distance, so the distance is equal to the rate times the time. So the distance that it's traveled for x would be its rate, which is 120, multiplied by 2 hours. So in 2 hours, don't turn this into a real complicated question. X is going to be equal to 240 kilometers. So that's how far it's gone in 2 hours. Now, some of these questions will tell you a specific distance, others no. And then we go on to the y, which is equal to a rate of 90 times 2 hours. So y is equal to 180. We now need to find z. And we're just going to get a new screen so I have a little more space. And z could be found simply by using the original equation, which links x, y, and z. So z squared is equal to x squared plus y squared. It may or may not be cooked up to give us a good, clean answer. But x we have to be 240. Y we have to be 180. So we push them through and we get an answer. So 240 squared plus 180 squared. And then take the square root of it. And of course we're in luck. So z is equal to, without doing a heavy calculation, equal to 300. Positive value only, because it's the distance between the two. So now we've got, I'll rewrite this equation down again. We have x dx dt plus y dy dt, and this is equal to z dz dt. So x, our 240, gets multiplied by dx dt, which we know to be 120, plus the y value is 180 multiplied by 90. That's equal to z, which is 300 times dz dt. So 240 times 120 plus 180 times 90, 45,000 divided by 300 should give us dz dt. So 150. So the distance between the cars is increasing at 150 kilometers per hour. Now, the next question is similar. In fact, the method is all the same for these. This is probably enough for you to go through them. But there's a few little things that you want to watch out for. So I'm going to go through these two next examples, even though they do appear so similar. Two straight highways are perpendicular to each other. So this is like before. One car is 3 kilometers from the intersection and is moving west at that speed, and the other one is moving towards the junction, and we want to get the rate that it's changing. So this is what the scenario is now. And it's pretty normal. X squared plus y squared is equal to z squared. So if you do want to pause me, feel free to do so and go through it. But we do want to get dz dt. And we want this at, well, let's just see. if there is any information on when this is going to be occurring. So we want to get it at x is equal to 5, and or let's back this one up, because we're actually, one car is, this is our x, and this is our y. So we want to get this when the car is 3 kilometers from the intersection. So at x equal 3, and y is equal to 5. So unlike the previous question, we don't have to solve for the distance. It's given to us. So as always with these, I'm going to differentiate first and start asking questions afterwards. There's our z. So 2x dx dt plus 2y dy dt is equal to 2z dz dt. Divide out the 2, and we get x dx dt plus y dy dt is equal to z dz dt. And, taking stock again, same as always, there's our dz dt, that's what we want. But here, when we're coming up with our x, our dx, and our dy, dx dt, based on this, it's moving west, so it's going to be 100 kilometers per hour. Always make sure your units are in order. Everybody in this case is in kilometers, so we're okay. But the other issue is going to be dy dt. This is where people make mistakes. Now you see that the car is headed towards the intersection. So that means that the distance is changing, is decreasing. So we need to be aware that the distance is always going to be, is dy dt, or it's going to be changing by negative 90. The negative matters. So you have to make sure you put that in there. Don't think of this as being on a coordinate grid, in which case it's moving up. Think of it as y refers to the distance from the intersection. So if you're moving towards it, it is decreasing at 90 kilometers per hour. Now we just add in all the values. So our x is equal to 3. Our dx dt is 100. Our y is 5. And then our dy dt is negative 90. And then our z. So we have to get our z, but that shouldn't be a big problem, because once again, going to the original equation, z squared is equal to x squared plus y squared. Z squared is equal to 3 squared plus z, or y, is equal to 5 squared. So 25 plus 9, z is equal to the root of 34. Now I'm going to keep this as this figure right now, and then I will decimalize it later, because this question does want us to take it to the nearest kilometer per hour. But just for ease, I'll keep it like this. So this right side of the equation is therefore equal to square root 34 dz dt. So 300 minus 450 is going to be our first calculation. So 300 minus 450 is minus 150, is equal to root 34 dz dt. And then when we do the division on that one, we'll get an answer. So 150 divided by square root of 34. And you should get something like dz dt is equal to negative 25.7. I'll get some more space in the next screen. But this is negative 25.7. We are asked to take it to the nearest kilometer per hour. So writing this out, we could say that the distance, between the cars is decreasing at a rate of 26 kilometers per hour. Now that sort of question, you can't intuitively come up with a negative or a positive value for it because it all depends on the relative motions of x and y. But in this case, the distance is decreasing. So watch the negatives. Let's do one more. And very similar, nothing outrageous with this. There's just one little thing. So 1 p.m., ship A is 25 kilometers due south of ship B. Ship A is sailing west at that rate, and ship B is sailing south at that rate. We want to get the rate at which the distance between the ships is changing at 1:30 p.m. So the illustration would look like this. It looks more like a canoe than a ship that's sailing downwards, but that's okay. And it started off, we need to be aware that if you called this ship A and this ship B right there, ship A starts off being right below but is going west, and then ship B is going straight south. So had ship A not moved, then you would be it'd collide actually. I'm going to call this X again. I'm going to call this Y for vertical, which is the convention, and Z like this. Now everything goes pretty normally, but we have to recognize that in this case the original distance between these two, the horizontal and vertical planes, is 25 kilometers. And that will matter. We still want dz dt. So x squared plus y squared is equal to z squared. So 2x, when we differentiate, dx dt plus 2y dy dt is equal to 2z dz dt. Divide out the 2's and you get x dx dt plus y dy dt is equal to z dz dt. So the issue becomes the values for x and y principally, because dx dt, we should have a measure for that. Now, because it's sailing away from what you would think of as being the intersection point, even though it wasn't called that, it's sailing away at 16. It's going away, so it's positive 16 kilometers per hour. And then y, or dy dt, well, in this case, the dy dt, because the distance is decreasing from that imaginary intersection point, we've got to be aware that it's going to be negative 20 kilometers per hour. So we have a negative value right there. Now that does take care of those two. But then we have to deal with the how far apart they are at that point, because x and y refer to distances. So we see that 130, this is all occurring at t is equal to 1/2 or 0.5. So 130 is half an hour after the original time. So there is a little bit of figuring out with these questions. And if you want to figure out how far x is gone, x will be, its distance will be 16 kilometers an hour multiplied by 1/2 an hour. So x is equal to 8 kilometers. Now the other thing, though, is y. Because to get y, you can't just multiply its speed of 20 by 0.5, which is just 10. Because you need to recognize that as it's going, y would represent the distance from the intersection point. And if you just went 20 kilometers an hour times 0.5, that's telling you how far you've gone. Now you can sort of figure it out in your head then by subtraction, but I'm going to set it up in one formula. 25 minus 20 kilometers an hour times 1/2. So that's 10. So y turns out to be 15. So be really careful with that. Easy to make a mistake. And then to get your z, z squared is equal to x squared plus y squared. So z squared is equal to 8 squared plus 15 squared. So if you do all the math on that, you should get z is equal to 17. So once again, we get a good number to work with. So I'll bring up the new screen, get some space, and then let's finish this one off. So x, I'll write this out, dx dt plus y dy dt is equal to z dz dt. So we have x to be 8 multiplied by dx dt, the rate that it's changing, which is 16. Then the y value is 15. dy dt is negative 20. And then our z value turns out to be 17 times dz dt. So multiply it out. 8 times 16. And then minus 15 times, oops, try again, 8 times 16 minus 15 times 20. And then divide by 17. So I'll put this in 2 steps, shouldn't be too complicated, but negative 172 is equal to 17 dz dt. So dz dt is equal to negative 10.1 to the nearest tenth. So the distance between the ships is decreasing at 10.1 kilometers per hour. So I'll stop there. I'll finish off these remaining related rate questions in the next lesson. So thank you for your time.